Okay, so welcome everybody, and thanks for coming. So in this session, what I would like to do is give you an introduction to data types and data modeling in functional languages, and specifically in the language F#. So this is what I would like to do. First, I'm going to introduce a simple problem, like an exercise, that we are going to use as an example. And then I'm going to do an implementation of that in C#, which is kind of, I will consider that kind of a common ground, which has a familiar syntax and concepts to everybody who worked with either Java, C# or JavaScript. And then I'm going to also mention some of the problems or challenges that we often face when we do data modeling in object-oriented languages. And then I'm going to introduce, kind of in contrast to the object-oriented approach, what kind of data types we have in functional languages, and specifically in F#. And then in the last part, I'm going to implement the same exercise, the same problem in F#. So this is the exercise that I would like to do. I would like to implement a data model to represent the cards in the standard 52-card deck, or also called the French playing cards. So who here is familiar with the French playing cards? The cards we play poker with, for example. Oh, almost everyone. OK. So just very quickly, every card in the deck can have a suit from the four suits. It's either a diamonds, clubs, hearts, or spades. And the cards can have either a value on it, a number, between 2 and 10. Or it can have a face on it, which can be one of the jack, the queen, the king, and the ace. And there is one special card, which is the joker. And that is special in the term that it does not have a suit. So this is the domain for which I would like to implement a model. And it is a really simple domain, but it has enough quirks to use it as sort of an example. And there are two additional requirements that I came up with for this exercise. The first is that I would like to implement this as a standalone data model, which is not tied to any algorithm or any logic. So we can imagine that I would like to implement this data model, and I would like to distribute it as a standalone library. And I want to use this to implement various different card games using this library. And we will see in a minute why this is an important requirement that we set out to do. And the second additional requirement is that I would like to adhere to domain-driven design. And especially, I want to adhere to two main principles. The first is to use terminology which is natural to the domain. So we've seen in the assignment that we were talking about the suits and value cards and face cards. And I would like to use the very same terms in the code as well. So if a domain expert looks at the code, it should feel familiar to them. And the second point which I want to satisfy, which is a suggestion by domain-driven design, is that illegal or invalid states should not even be representable. So the data model and the type system that I create should not allow an incorrect data to be even created. And the reason why this is important, because this can help in avoiding having to write a lot of validation codes or error handling codes or code that has to take care of missing data or incorrect fields. So let's see how we would implement this in C#. I chose the language C# as a common ground because this is what I'm the most experienced with. And also, the syntax of C# will be familiar to everybody who worked with Java or JavaScript. So the first thing I want to do is to implement something that will represent a suit of a card. And in C# we can use an enum to do this. And the four suits are clubs, diamonds, hearts, and spades. And similarly, we will also have to represent the different faces. And I will also create an enum for that. I will call this face. And that can be the jack, the queen, the king, and the ace. So in C#, the type enum is something that can only have one value out of these options. So if you create a value of the type suit, then you can choose from these 4 values which one you would like to use. So it's sort of like 4 constants, basically. And now with these 2 types, we can actually implement our class, which will represent the card. I'm not going to focus on representing a whole deck of cards. I'm going to focus on only a single card. So first, let's create kind of a naive implementation, and let's see how far we can go with that. So I will implement a class called card, and every card has a suit. So I will add the property of type suit. Its name is also going to be suit. And then a card can be a face card, so I will need a property also to store what is the face of the card. I will add another property. Its type is going to be face, and its name is going to be face as well. And the card can also be a value card, so I will add a property that will represent the value, and I will just use simply an integer to do that. And now that we have this type with these 3 properties, the way I can create an instance of this type is to just specify the values of the various properties. So I will say I create a card which is, let's say, 2 of clubs. So I will set the value to 2, and I will set the suit to clubs. There is one big problem with this data model at its current state. And what that is that in C#, enums and integers are value types. And what that means is that if we don't specify their values, they are not going to be empty. They cannot be like null, but they are going to have a default value. And in case of an enum, if we don't specify it, it's going to automatically just take the first value of the options. So in this object, the value of the face property is going to be Jack, because that's the first value of the enum. So if we are passing this object to somebody and they want to process it, they want to figure out what kind of card it is, they will not be able to use this in a meaningful way, because both the value property and the face property will be set to a meaningful value. So you will not be able to decide whether this is a 2 or whether this is a Jack. The way to solve this in C# is a feature which is called a nullable type. And we can do this by adding a question mark after the type. So I can say that both the face and the value property are nullable. So by default, their values are null. And that is getting now better, because now this object is meaningful. If we pass it to somebody, they can check whether the face or whether the value is null or not. And based on that, they can decide whether this is a value card or a face card. But there is still something that we don't satisfy from our requirements of making illegal states not representable. Because I can still simply set the face property as well. So I can say that the face equals to face.jack. And now I'm in the same problematic situation that the 2 of clubs object represents an incorrect value. There are multiple ways to solve this in C#. The way I usually solve this situation in practice is to first create a constructor for this type, which is going to be private. And what this means is that nobody will be able to call this from outside. We will be able to call this only from inside. And in this constructor, I will accept an argument for all of the properties that we have. And in the implementation, we will simply set the properties to the specified values. So this constructor is not called from the outside. And in order for other callers to be able to create instances of this type, I'm going to introduce public factory methods. And I'm going to introduce two methods, one for creating a face card and another for creating a value card. We'll call the first one create face card. And it will have two arguments, the face and the suit. And notice that here in the type, I'm not using the question mark notation because this input argument does not have to be nullable. It always has to be provided. And what I have to do in this factory method is just simply return a new, object using my private constructor. And to the value argument, I can pass in null. And I will create a similar factory method for the other case, the value card. And this have to take an integer as an input. And I have to adjust the constructor call. So the face is going to be null. And instead of that, I'm passing in a value. So now this code is getting a bit further because this constructor call is not going to compile anymore. The compiler will not allow us to do this because this type does not have a public default constructor anymore. So I'm forced by the compiler to use these factory methods. So instead of this call, what I have to do is card.create value card. And I will have to say that this is a 2 of clubs. And this is nice because this, at the time of creating a new object, forces us to do the right thing. And also the code becomes slightly more expressive. It's self-documenting what we are trying to do. So there is one other thing that is missing from this solution. So now we are enforcing at the time of the creation to create correct values. But these properties that we have here, these are mutable. We can change their values after creating an object. So nothing is stopping us from saying after the creation, 2 of clubs.face equals face.jack. And now we are again in the same problematic situation. We have an incorrect object that is not meaningful. And the reason for this is in C#, we tend to, by default, when we create properties, we tend to write both the get and the set methods for them. And what that means is that they are going to be mutable, so they can be changed after an object is being created. Solving this is really simple. We can just simply remove the setters. Oops. And if we simply remove the setters, then this line of code is not going to compile anymore. The compiler is not going to allow us to mutate the values of this type. And actually, simply omitting the setter is a relatively new feature in C#. I think this was introduced in C#6. Prior to that, it would have taken a bit more code to do the same thing. So this type now satisfies what I set out to do. We cannot create an incorrect instance of this type. And because it's immutable, we also cannot change its value afterwards. And there is one last thing that I kind of forgot about, and that is the special case when the card is a joker. We still have to represent that somehow. The way I'm going to do that is simply I'm going to add a new property which will have the type Boolean, and I will call this isJoker. And what I say is that if this is true, then the card is a joker, and I will ignore everything else. And I have to adjust also my constructor to do this. And I will set its value. And similarly to this, I will need to adjust these calls. So I will pass in false, because this is not a joker. This is not a joker either. And I will need a new factory method to create jokers. And the jokers do not have a face or a suit, so I don't need any input arguments. And I will say the first argument is true, because this card is joker, and the face is null. And we have one question. What do we want to do about the suit? Because the suit is not nullable, so it will have a value automatically. And here we have two choices. We can either leave it as it is, and we will say that if is joker is true, we will just ignore the suit because it doesn't matter. Or what we could do is we could make this nullable as well to make that decision more explicit. I'm not sure which solution would be the better. I don't really have a preference. I would just leave it as it is. And what I will say here is I will pass in default suit. And what this does, it basically just takes the first value of the enum. So in practice, this is going to be clubs. But this is the kind of situation that what I don't really like when I'm doing data modeling in object-oriented languages, when I feel that I have multiple different approaches, but none of them seems to be clearly better than the other, and both of them feels a bit like a hack. So I kind of feel that the language and the type system is not holding my hand. It's not trying to help me to express what I want to do. So now our data model is complete, and it can represent everything that we want it to do, and also it can represent only valid values. So let's see how we would actually use this type to implement some logic in this domain. And I added an example to this slide. This is actually the calculation of the scoring in the card game Rummy. And this is complicated enough so that we can have like an example of what it would look like. And these are the basic rules. So when we are calculating the scoring, we calculate an integer for a card. And if the card is a queen of spades, then we have to return 40. For any ace, we have to return 15. Any other face card, we have to return 10. For tens, we have to use 10, and everything else is 5. So this is what I would like to implement. So let's create a method returning an integer. I will just call this calculate value, and it takes a card as an input. So first, I want to take care of the first 3 cases in case of a card being a face card. So I will say if card.face has value, and what this checks in C# is that this property is not empty. Then what I would like to do is if the card is a queen and the suit is spades. This was our first case. In this case, we have to return 40. Do I have a bug? Where? Thanks, good point. So in this case, we have to return 40. Then if the card is an ace, we have to return 15. In case of any other face card, we have to return 10. Thanks. And now we took care of the first 3 cases. And the other 2 cases were if the card's value is 10, then I have to return 10. And otherwise, I have to return 5. So this is what business logic would look like when implementing this type. And I didn't take care of the joker. I'm not sure if that's a valid card or not. We could either return 5 or 0 or throw an exception. I'm not sure what that would be in Rummy. So this is what the implementation of this problem looks like in an object-oriented language. And there is one extra thing I want to show. So you might be asking, if we are using an object-oriented language and we have multiple different options, why are we not using inheritance to solve this problem? Because that's a typical solution in object orientation. And I was thinking about that, but I think inheritance would be a bad approach in this particular scenario, because what it would look like is something like this. So we would have an abstract base class called card, and then we would have a joker derived type, and then we would have another abstract base class called card with suit, which would define the suit property, and then we would have two actual non-abstract types, the face card and the value card, and these would add the face and the value properties. Now, I have two main problems with this approach. One is that implementing the same business logic to calculate the value of the rummy card would look something like this. So we would have an implementation maybe in the joker type. So I will say here, calculate rummy. And then we would have a different implementation in the face card, and also a different implementation of the value card. So the logic for handling one single card game would be kind of scattered around multiple different classes. And it would be much more difficult to get an overview like this of what the logic looks like. And another problem that I have with this model is, if we want to implement a different card game, let's say poker, then in this case, we just implement a different method, which can be in a completely different library. And all of my business logic can be separated from each other. But in this model, what I would have to do is I would have to add another method here called calculate poker. And this tends to happen in object-oriented models quite a lot, that classes just grow and grow and become very big as we add more and more functionality. So these are my two main problems with the inheritance-based model, and this is why I think it's not a good approach in this scenario. Yeah, so what I was mentioning is that in object-oriented languages, if what we have to do is write code which checks the dynamic type of the card, I could technically do that. I could say in C# if card is, and then use a type like joker or face card. This is usually considered to be an anti-pattern, at least based on what I have read about the topic. So if I want to implement business logic in this style, then I much more prefer to have a proper type, which is not based on an inheritance model. But technically that's an option. And actually, in the latest version of C#, they even added a language feature which kind of does the same thing. So what you can say is something like switch cards, and then, yeah, like a very basic version of pattern matching, and then here you can specify cases based on the types. But this is a feature that's quite a lot debated on the internet, specifically because of the reason that I mentioned, that it is, in some places it's considered an anti-pattern, and now in C# it is explicitly introduced. So it's a bit controversial. So this is just an overview of what we saw in the object-oriented implementation. So immutability was not a default. We always have to work in C# to get immutable data types. The either relationship is not easy to express. So if we want to say that an object can be either this or that, or one of multiple choices, we have to actually write code to express that. And the last point is the one that we were just talking about, is that if we are using an inheritance-based class hierarchy, that does not play well with pure data models, which we want to isolate from business logic. So let's see what we can do in functional programming languages to implement a similar data model. Generally, in functional languages, data types tend to be immutable by default. And the type system in these languages have very powerful composability capabilities. So types can be very freely composed together. And objects in functional programming tend to have value semantics. And what I mean by this is, in functional programming, the way we think usually is that we have a function that takes an input and then produces an output. And in the meantime, it does not have any side effects. So the things that we are passing in and we are getting as an output, they are just values and not entities which are mutated. On the other hand, in object-oriented languages, what we often have is we create an object and we think of it as an entity, and we pass it around, and then multiple actors modify its value. And in functional programming, we don't tend to do that. And the last point is just an interesting detail, is that data types in functional languages tend to have like a scientific background related to mathematics, mainly in set theory and category theory. So let's see what kind of data structures we have specifically in the F# language. The first one that I want to show is the record type, which is very similar to just a class or a struct, or in JavaScript, just to an object. One thing that makes it special is that it's immutable by default. And when we create a value of a record, we must specify the values of all of the fields. We cannot leave any fields empty. And technically, in the background, it is implemented by immutable reference objects. So when we are passing around a record, it is not copied, but only the reference is passed around. But because they are normally immutable anyway, they have value semantics, so we don't really think about copying or passing by reference that much in F#. And I mentioned that by default it's immutable, but if we want to, we can make a record mutable. And this is an example of trying to change the value of a field of a record. So we have a record type called person, which has a first name, last name, and age. And we are creating a value of that type called p and setting some values. And in the last line, we are trying to mutate the value of the age field. And that line is not going to compile. The compiler is going to tell us that that field is immutable. And what we can do is we can mark a field with the mutable keyword. And if we do that, then the mutation in the last line is going to work. So it is kind of the opposite of what C# is doing, because in C#, everything is mutable by default. And if you want to make it immutable, then you have to opt in. And in F#, it's the other way around. And also, one thing that you might notice is that the syntax for changing the value of the field is not the equal sign, but this left arrow operator, which is a much more special syntax. And that is also trying to communicate that here we are doing something special that we don't usually do. The only situation when mutability in F# is important is in a high-performance scenario when you want to optimize something. That is the situation when you might need this, but normally we don't use mutable fields in F#. The second basic data structure in F# is the tuple. And it is similar to tuples in other languages. It's basically just multiple arbitrary number of values put next to each other. The one nice thing about tuples in F# is that their syntax is very nicely built into the language. So in order to create a tuple value, we don't have to do any type declarations. So you can see two examples in the first two lines. We are creating a point that is a tuple of two floating point numbers. And then we are creating another tuple, which is a tuple of a string and an integer. And we can just simply write values next to each other, separated by a comma. And we don't have to specify the types explicitly. And in line 4, you see a very simple representation of the feature called pattern matching in F#. So what we are doing in line 4 is we are extracting the two values from the point tuple. And this is a pretty generic syntax that we can use in F# to process tuples. So in the first 3 lines, we don't see any type declarations, but in other situations, we we can use type declarations if we want to. So if we design a data model, then we can explicitly say that, for example, a type of a field is a tuple type. And the notation to declare a tuple type is to use the asterisk character between types. So the myTuple type is a tuple of a string, an integer, and a person. And the notation of using an asterisk might seem a bit unusual. Why is that symbol used to notate a tuple? And this is related to what I mentioned, that these data structures have some background in mathematics and in set theory. And I can illustrate that with an example for the tuples. So if we have two types called A and B, and A has 3 different values and B has 2 different values. So we can think of those types as enums. They only have a handful of fixed values. So if we create a tuple of those 2 types, then the resulting tuple type is going to have 6 different values, which is all the different combinations of the input values. So creating the tuple of 2 types is basically equivalent of the Cartesian product operation in set theory. And because of this reason, a tuple in other languages is also called a product type. And this is where the asterisk symbol is coming from, because it's the symbol of the multiplication, basically. And I just wanted to mention it first because it's interesting. And the other reason is, if you are looking at some other functional programming language, they might be talking about product types. But what that means is just a tuple, basically. The last basic data type that I would like to introduce in F#, and I think this is the most interesting one, is a discriminated union, which is sort of a fancy name, but the data type itself is very simple. So basically, a discriminated union is a choice of multiple different options. So the thing that you see in the slide is, for example, a choice of various different logging levels. So far, this looks very similar to C# enums. For example, in C#, we used an enum to represent the suit or represent the face. The thing that makes discriminated unions more interesting is that besides having these different options, every option can also have a value associated with it. Let's look at an example what that would look like. So here we are creating a discriminated union called shape, which has 2 different cases. One is a circle and the other is a rectangle. And both of them have a value associated with them. The circle case only has 1 float associated with it, which is the radius of the circle. And the rectangle has 2 values, a width and a height. And well, actually, technically, the rectangle also has 1 value associated with it, but that value is a tuple of 2 floats. So this is a situation in which tuples come in very handy, and also we have to use the asterisk notation to express the tuple. And what you see, and I didn't mention it on the slides about tuples, we can also give the tuple values a name if we want to. For example, here we are calling it radius and width and height. And in the last 2 lines, what you can see is how we create actual values of this discriminated union. For example, I'm creating a circle, and then I have to specify only 1 number. And then I'm creating a rectangle, and then I have to specify 2 numbers. And if I want to be explicit, I can use the names which are specified here, but these can also be omitted. Yep?
It's related to shape type.
Oh, yeah. So you mean that you would expect to see here something like shape dot circle, right?
On the left side, like circle, you need to specify something like because.
Yeah. So if you wouldn't have this type declaration,
Yeah.
you could not use these terms here at all.
Okay.
And also, the reason why we define it as a discriminated union is because we want to handle shapes in kind of unified way. So for example, you can imagine you can have like a list of shapes. And every shape in that list might be either a circle or a rectangle.
I'm asking,
Yeah.
should somewhere put this is a type of shape, like circle type of shape equals circle, or rectangle type of shape equals rectangle.
Yeah, I understand what you mean. So in F#, when you create a value, you don't have to specify the type here. The compiler is going to figure out that this value is going to be of type shape. So this is not of type circle. Circle is not even a type. And actually, if you would have two different discriminated unions and both would have a circle case, I think the compiler would either give you an error, and then you would have to use some other syntax to specify it, or it would just take the first. I'm not sure about that. But if there is no unambiguity, or ambiguity, then you don't have to specify the name of the union itself. So this is what it looks like to define a union and to create union values. And let's look at how we can actually use them. So let's say we want to implement a function which calculates the area of a shape. And what we can use to do this is the feature that I mentioned, which is called pattern matching. So with the match shape with syntax, we can start a pattern matching expression. And then we can decide what we want to do in the various different cases of that value or of that union. And we say that if the shape value is a rectangle and it has these two values associated with it, then the result is just going to be W multiplied by H. And if it's a circle and the radius is R, then we are just calculating the area of a circle. And then this is how I would actually call this function to do this calculation. So I mentioned that tuples have this relationship to the product operation in set theory. And discriminated unions also have a similar relationship with another operation. But in this case, that operation is actually the discriminated union operation. So that is where the name comes from. And here is a similar example with the same two types. So we have the types A and B. And if we calculate the union of those two sets, then the resulting union set is going to have 5 elements. And that is why this operation or this type in other languages is sometimes called a sum type. I think in Haskell it is called a sum type. I'm not 100% sure about that. But you might see this name in other functional languages. So now that we have these 3 basic data types, the record, the tuple, and the discriminated union, let's see how we can implement the same exercise in F#. I'm going to start the same way. I'm first going to specify a type for the suits and the faces. And I mentioned that discriminated unions can be used without a value. So this is a suitable solution for the suits and the faces. So I will say I have a type suit. And it can be clubs, diamonds, hearts, and spades. And I will also have a type face, which can be jack, queen, king, and ace. And now what I want to do is I want to implement the actual type that will represent a single card. And we talked about how a card is basically a choice of multiple different options, and every option has a different value associated with it. So a card is either a joker, and then it doesn't have a value, or it's a face card, and then it has a suit and a face, or it's a value card, and then it has an integer and a suit. And actually, this is basically what discriminated unions can do with an associated value. So I can simply say type card. It's either a face card, and then it has a face and a suit, or it's a value card, and then it has an integer and a suit, or it's a joker. And if it's a joker, then it doesn't have any data associated with it. And now let's say how we can create actual values of this type. So I can say 2 of clubs equals value card with 2 and clubs. And here we don't have to specify the name card. And here we don't have to specify the name suit. The compiler figures that out if it's unambiguous. And let's create another card, which is going to be, let's say, the queen of spades. And this would be a face card with the queen and the spades input arguments. And one thing to note about discriminated unions is that there is no way to kind of mix 2 different cases together. The value of a discriminated union is it can be only one case. So there is no way to mess that up. And also, these values are inherently immutable. So there is no way to change their values after creation. So actually, with this data type, we can express all of the different cards that we have, and we also satisfied our requirement to making illegal values not representable. So basically, with these 4 lines, we expressed the same thing for which we had to write this piece of C# code to kind of express. And now let's see how we would implement our same business logic function for calculating the value of a card in the rummy game. So I will create a function called calculate value, and it will take a card as an input. And I can use pattern matching to handle the different cases. So I will match cards with, and I will bring up the specification again. So let's take care of the first 3 cases first. So if it's a face card with queen of spades, then the value is 40. If it's a face card and it's an ace, and we don't care about the suit, and that can be expressed in F# by using an underscore, then it's 15. And if it's any other face card, and then I don't care about any of the values, then it's a 10. And with these lines, we expressed the first 3 cases. So we took care of all the face cards. And one interesting thing that I would like to show is Visual Studio now underlines the card word, and it displays a warning to us. And what it says is that this is an incomplete pattern matching expression. So there are possible values of this union that we did not take care of yet. And this is a very handy feature of the F# compiler. Currently, this is a warning, but it can also be configured to be an actual build error. Because if you imagine having a complicated data model and having many different parts of your business logic depending on it, and then you extend that data model with a new feature or with a new property, you always have to remember to update all of the code that depends on it. And the compiler cannot help you figuring out if you forgot to adjust all of your logic. And in F#, it can be really handy that the compiler can check if you are always handling all of the different cases that unions have. So let's take care of the rest. If we have a value card, which is a 10, and I don't care about the suit, then the output is 10. And in any other case, we are returning a 5. So this is what pattern matching looks like in F# with unions. And just to see if it really works and I didn't make any typo, we can actually execute this code in Visual Studio Code. But to see the actual results, I have to call this method. So I will say value 1 equals calculate value, and I pass in first the 2 of clubs. And then I do the same thing with the queen of spades. And in F#, this syntax actually calls the function, so I don't have to add parentheses around the arguments. And I can use the send file command in Visual Studio Code. And you see that in the terminal, it compiles all of our code and then executes the 2 lines. And it calculated the first value is 5, and the queen of spades is 40. So this was the implementation of the same exercise in F#. And this example might seem a bit specific, but actually these discriminated unions pop up all the time in general domains, in all sorts of business logic. And finally, let's just look at a couple of examples of what other things can be nicely represented with this kind of data type. So the first one is a type which is called operation result. And we can imagine that this is, for example, retrieving a piece of data from a database or from a network call. And the 3 cases that we have is that it can either be a success, which has an associated data with it, or it can be a not found, and in that case, it doesn't have any data, or it can be an error, and in that case, it has an error message. And I think this is a really nice and expressive data model, because, for example, what we tend to do in C# is if it's a success, then we return an object. If it's not found, then we maybe return a null. And if it's an error, then we maybe return a null, or we throw an exception. But there is no real way to figure that out without reading the code or reading the documentation. So the type system itself does not express these concerns. And the second example is, for example, the input to an HTTP request. So an HTTP request is either a GET or a POST. And if it's a GET, then it only has a URL. And if it's a POST, then it has a URL and a body. Well, of course, this example is somewhat simplified. And the last example is, for example, specifying credentials. So our credentials are either username and password. And in that case, they have 2 strings. Or the credentials is a certificate. And in that case, it has a path to a file. Or the last case is we are not using any credentials, and that doesn't have any data. So this is a data type can be used in many different scenarios. And then the compiler can really nicely help us to make sure that we are handling all the different cases that we have. So this was all that I wanted to show to you. And I added a couple of extra resources to the last slide if you are interested in more information about this topic. Thank you.